Hello, everyone. My name is Brendan, and I'll be presenting today. So I originally didn't plan on giving this talk online or remotely. However, because of a global health crisis, we have been pushed to do IEEE VR in virtual reality. And this brings to focus some of the research I've been doing because we had to make a choice between presenting over Zoom with a webcam feed like we're doing now, so you can see my gestures, and some of my rich, nonverbal social cues, or to use Mozilla Hubs to have a sense of social presence in a shared virtual space, but to get rid of some of these subtle cues. And we as a VR community know that we shouldn't have to choose between them. In the future, we won't have to. So here, let me play for you a video from Facebook Reality Labs, where I'll be an intern this coming fall.
What do you do for exercise?
I do yoga and then I do boxing too.
What kind of
And
yoga? Wait, okay,
yo-
yoga and boxing.
yeah, there's a nice
So the future is very rich, and the eyes play a very big role in this, in the eye movements of your social virtual avatars. And to do this, we need to use eye tracking technology. And as more and more users go into this type of technology and use these devices, we're actually subjecting them to a very simple security vulnerability. This vulnerability is the iris pattern that's imaged by an eye tracking camera, seen here, contains the iris pattern, which can be used as a biometric. We assume a very simple threat model with this type of work. We have an untrusted eye tracking platform or system. So what this means is that the head-mounted display or the wireless connection you're using to stream data for processing could be compromised. We assume that an adversary would want to steal your password and essentially spoof your login using this biometric. So for example, let's say the adversary gains access to the data port used to transfer the eye images and saves them. They can then use these images to log in for you. And it hasn't happened yet, but hypothetically this could occur with the Microsoft HoloLens V2, which already enables you to do iris authentication through the eye tracking camera to your Microsoft account. Now, this is both a feature, but it's also a huge security risk. In a way, we're streaming your password in plain text at 60 frames per second, and this is not good. So, of course, there's some related work in this area. For augmented reality in general, people have looked at what malicious inputs and outputs to display could have an effect on the user. For example, would rendering some object make somebody trip and fall suddenly? In wearables in general, there's been a lot of work with the privacy of bystanders, and you saw this when the Google Glass came out. So a lot of restaurants banned them because you didn't know when they're recording images or video. In terms of eye tracking, folks have researched the privacy of the scene camera, similar to the wearables case, as well as publicly released data sets that have aggregate data that claims to be anonymized, but does have individual identifiers. And we have our prior work last year at ETRA 2019, where we proposed a method to secure the iris biometric within eye images, like you saw on the previous slide. And in this work, we had a slightly different threat model. We assumed that you could trust the eye tracking platform, that is the head-mounted display, but that you couldn't trust third-party applications that access the raw image stream. Broadly speaking, our research problem is to say, how might we transform this eye image to turn off the biometric or secure the iris signature? An insight that we had in our past work is that the features used for iris authentication and the features used for eye tracking are separable in the frequency domain. So the actual pixels that represent these features, seen here in the plot for the iris pattern as a spike that goes up and down, or a pupil that lies flat and dark, or a glint that looks like a Gaussian bump, have different frequency components. The iris pattern is a high frequency component, while the eye tracking features are low frequency. And of course, in the paper, we present a bit more of a theoretical basis about how this works and how we can use a low pass filter, so essentially letting in just the low frequency eye tracking components and not letting in the high frequency iris components could be used to filter out your biometric and secure your iris. In this work, our key insight is that we can do this in hardware using optical defocus. And this is quite simple. So here's a typical eye tracking configuration. On the left, we see that the eye camera is positioned close to the user's eye. However, our invention is to drag the eye camera as far as you possibly can away, blurring the image and blurring the iris pattern itself. And what this does is, with the increased distance, adds optical defocus. You can see this in the images below, where the close has a nice iris pattern, while the far distance has a blurred iris pattern. This is simple to reverse, and the user can control this. They don't have to go do anything in software. They can just reach up, drag the camera down, and put it back whenever they want to. So our first contribution is to explore how much blur is enough in this type of secure configuration. On one hand, we can of course have no blur. So you see that we get reasonable gaze accuracy. Our gaze error is less than 1.4 visual degrees. Well, we also have a CRR, which stands for correct recognition rate of 79%. So correct recognition rate stands for how many images of this stream could be used to authenticate you as the user. So just about 4 in every 5 image frames, if stolen, could be used to authenticate as you. On the other extreme, we would have too much blur. And you'll see that I've quantified blur in terms of sigma and pixels in this work. So in the paper, we present a method to take the camera distance in millimeters and map it over to this sigma blur parameter. But what we're seeing with too much blur is that eye tracking is no longer possible because we blurred away all of the features of the pupil that we track to do eye tracking. However, we have completely secured the iris pattern as we have a CRR of 0%. So what we're finding is somewhere in the middle, there's a sweet spot around sigma equals 3 pixels, where you still get reasonable gaze accuracy. So our gaze error is less than 1.9 visual degrees. However, we've drastically reduced the CRR from 79% down to 5%. So to evaluate this configuration that we presented, we recruited 15 participants and had them perform an eye tracking task in both configurations. So on one hand, we looked at the security. So again, the y-axis is the correct recognition rate, what percentage of frames could be used to authenticate the user. And the x-axis is sigma, or our blur parameter. And for each individual, you'll see a gray cross indicating what their value was. And what we're seeing is after a value of sigma equals 3 pixels, the correct recognition rate lies below 5%. On the other hand, when we explored the utility of this, we presented 5 circular targets on screen and computed the gaze accuracy. So here you'll see the gray crosses again, but you'll also see gray circles. And these stand for the in-focus configurations, or an ideal eye tracking setup. And what we're seeing is that the accuracies are not that different in the secure configuration compared to an ideal tracking scenario. We still have an accuracy, an error, less than 3 degrees visual angle in this type of setup. So that's great. We've showed that you can secure the iris pattern. However, what impact does this have on social VR and your virtual avatar like we saw before? Because we've quantified this error, it doesn't mean that you're going to have as natural eye movements. So we wanted to explore this with perceptual studies. We broke this into 2 research questions. The first is at what level of blur do viewers notice a difference in the animation of an avatar's eyes relative to a reference? And we studied this using a detection threshold by essentially comparing unblurred reference avatar animations to the animations generated from blurred data. Our second research question is, okay, so if you did notice a difference, does it actually degrade your interaction with the virtual avatar, or does it have no effect at all? So to generate the stimuli for this, I had to wear the eye tracker and generate conversational gaze data. And what I did is I watched an English as a second language video where they were given English phrases and I had to repeat them back. To do this, I simulated the conversation, collected the data, and then we transferred it to a virtual avatar that you can see here. And this virtual avatar, you can see is not stylized or cartoony, but is actually somewhat realistic. And we did this on purpose because we know the more realistic an avatar looks, the more accurate their subtle cues, like eye movements, must be for it to look like a natural, real avatar. We then collected the eye images and blurred them systematically with a Gaussian blur kernel of several different values. And we did this to put them through the eye tracking pipeline and regenerated the eye animations for different levels of blur mapped onto this virtual avatar that you see. So here's an example that you could see from our study. And we called it the same different study. Essentially, they would see these 2 videos playing side by side and have to tell us whether they're the same or different. So here I'm going to play the stimuli, and please focus on the eyes. So for this stimuli, blurred eye images of sigma equals 5 pixels were used to render the animations on the right-hand side. Now for the actual study, we presented more than just 1 animation per level of blur. We actually had 60 total trials. So we had 6 animations, 5 different levels of blur, and 2 different orientations. Essentially, the blurred video could be on either side of the screen for those participants, and we repeated these trials. So as I was explaining, our method involved the same different task, and we had 20 different participants recruited. Each of them would see these trials with reference unblurred eye image animations and eye animations from blurred eye images next to each other. And we recorded for each one a response of same or different. And what we used this data for was to fit something called a psychometric function. And what this stands for is, as input on the x-axis is a level of blur, so a different level of stimulus. And on the y-axis, we have the same percentage. So essentially a function says for a certain level of blur, what is the probability that a viewer is going to notice a difference or not? And you can see we have individual responses as the gray dashed curves, as well as an average response as the bold white line. And within this, we study a few things. So the first of that is the PSE, or the point of subjective equality. Essentially, this is the rate where they are answering at the same point of chance. So in this case, 50%, because there's two options. So they can't consistently tell if the stimulus is there or not, or if there's a difference, essentially. We also compute the detection threshold. So we do this at 25%, same rate. And this is the point where they're consistently noticing a difference. So 75% of the time, they are telling us there's a difference between the two animations. And going back to security, when we think about this, our PSC was at sigma equals 3.5 pixels, where we had correct recognition rate less than 5%. Our detection threshold was equal to 5.6 pixels, and where we had a correct recognition rate of less than 2%, which is quite secure. So that's great. We've seen that there is a difference and there is a detection threshold for a certain level of blur within avatar animations. But does it actually impact the interaction that you're having with this avatar? So to do this, we recruited 19 different participants who hadn't participated in the same different study or seen any of these avatars before. And we had them watch individual videos in the middle of the screen. They then had to rank several characteristics on a 5-point Likert scale, such as the avatar was truthful. We used 5 different characteristics for this. So the first was truthfulness. We also explored naturalness, attentiveness, comfort with your interaction with the avatar, and the level of eye contact. All very important social cues. And what we can see by these box and whisker plots is that the median value and the median response degrades for higher levels of blur, as expected. So thinking about social VR, there's 2 properties that we could focus on, attentiveness and truthfulness. These could apply to a conference presentation, like I am doing right now. This could apply to a virtual job interview that you're having to try and get a new job, or just interacting with family and friends. You want to retain these social characteristics of yourself if you're using a social avatar. And what our takeaway is after sigma equals 3, starting at sigma equals 5, we see a change in these perceived attributes. They start to degrade. And we remember that at this point, past sigma equals 3, our correct recognition rate was less than 5%. So ultimately, we recommend that you use a blur kernel for this type of social VR application between sigma equals 3 and sigma equals 5 to somewhat retain your social interaction while also adding a level of security for the users of the system. So to come back around to our research problem, we found that you can use defocus or blur to secure the iris biometric within eye images. This can be done in software with Gaussian blur or in hardware with optical defocus like we showed. And this can apply in many eye trackers that are used in VR and AR headsets today. And lastly, the parameters and blur parameters you select for this do impact the utility in the application you're doing. So we studied the security utility trade-off for social VR. However, this could apply to any eye tracking application in AR and VR, such as foveated rendering or gaze-based interfaces. So of course, our study had some limitations. In the experiment, only the eyes of the avatar were animated. This meant there was no pupil dilation, blinks, or mouth movements. So as part of this, we plan to run future perceptual studies with these cues added into the signal. Our security framework itself assumed that the eye tracking camera was accessible, that the user could reach up, grab it away, adjust the focus, and do something with it. And this isn't always the case for VR and AR displays. Some of them are embedded within the display for the eye tracking technology. So as future work, we want to generalize the solution and find a way to instantiate it for different eye tracking configurations that apply today. And last, which I think is one of the most important points, is that we've only studied a fixed security and fixed software for eye tracking. And while we did use a standard method for iris recognition, month by month, new researchers are coming out with deep networks that become state-of-the-art, and it's constantly evolving, as well with eye tracking methods. And what we've done is, in a very fixed, discrete way, compute the security utility trade-off. But in the future, we want to generalize this framework as an adversarial learning problem. So given a certain authentication system and a certain eye tracking software, could we optimize and find this blur parameter automatically and in a general method that will adapt to future technologies? So that about wraps it up. Thanks for your time. And I would like to acknowledge NSF for funding our work. And please read our paper and visit the website for more details. Thank you.